lectures. Today we will learn about independence of events. So first of all, I want you to have a look at an example to find a probability of A given B. In this testing, when you have assumption that the outcomes are equally likely for the left picture and the right pictures. So how can you compare the probability of A given B and probability of B in the left picture and in the right picture? So the code is here. So this is the code for answer the first question. No, you just scan this code and you can answer.
Like if I don't answer.
No, that's why it just have you to engage in during the lectures. Okay. Is question 5 and question 6. Will you mark in the question? Yeah. No. No. This one is just for you to practice what you have learned from previous lectures and for another activities in the class. Okay. So to compute probability of A, so you just count how many elements in A and divide it by the total element in the sample space, right? And how to compute the probability of A given B, just compute the element of the intersection between A and B divided by the element in the set B, because they are equally likely outcomes. So that's it. Okay, so here is the answer for probability of A given B. The probability of A given B the probability of A given B in the left hand side pictures equal to probability of A intersect with B divided by probability of B. This is the definition of conditional probability, right? And how many elements in the this intersection, which is 2. This is the intersection, right? So you have 2 over 5. 5 is the element number of elements or in B. And in the right hand side pictures for probability of A given B is 2 over 5, the same, but the probability of A is 2, 4, 6, 8 over 20, which is 2 over 5. And in the left hand side picture, the probability of A is 9 over 20, which is different from, in the left hand side picture, probability of A different from the probability of A given B. In the right hand side picture, you have probability of A equal to the probability of A given B, which means that probability of A given B doesn't change the value compared with probability of A, right? So even this is a conditional probability, but it's still the same value with probability of A. So we call this phenomena is the independence. A and B are independent. If you have probability of A given B equal to probability of A. So in the left hand side, in the right hand side picture, we have probability of A given B equal to probability of A. Okay. Okay. One more thing is that if you have probability of A given B equal to A, probability of A, then you can deduce that, okay, I can write it here. So this one means that if I have probability of A given B equal to probability of A, then I can prove that this one equivalent with probability of A intersect B equal to probability of A times probability of B. Right? This one is quite obvious when you use the definition of conditional probability. So if you have the left-hand side, the equality in the left-hand side, then you can use the definition of conditional probability. Then you have probability of A given B equal to probability of A intersect B divided by probability of B, right? And because this one equals to probability of A, which means that you multiply both sides for probability of B, then you have this equivalent with probability of A intersect B equals to multiply both sides of this equality by probability of B. Then you have probability of A times probability of B. All right, and this is equivalent. So, and another equivalent form is that this one also equivalent to probability of B given A equals to probability of B. And the proof is also the same, because probability of B given A equals to probability of B intersect A divided by probability of A, and then you multiply both sides for probability of A, so you still have probability of A intersect B equals to probability of A times probability of B. So then now we go to the definition of independence. So A and B are said to be independent if we have probability of A intersect B equals to probability of A times probability of B. So wherever you have this equality, the yellow equality, then you can say that A and B are independent. So this is the definition of independent. Okay. Do you have any questions about independence? All right, so we have first question 7 and 8. So what is it? Question 7. A and B are independent if and only if A and B are disjoint. Is it true or false? False. For any case. What do you mean? Huh? Not for every case, yes. So then answer question 8. When the statement in question 7 true? Yes. So when, okay, so we have the statement A and B and A, okay. For question 7 say that, can we say that A, B, independent if and only if A and B are disjoint? This is true or false? Okay, when A and B are disjoint, which means that A intersect B is an empty set. So probability of A intersect B is 0, right? And A and B independent, from the definition of the independent, we have A and B independent when you have probability of A intersect B equals to probability of A times probability of B. So if you have A and B disjoint, so probability the left hand side of the yellow equality is 0, but the right hand side in some cases maybe not 0. So this is an example. So for example, this is A, this is B. Even A and B are disjoint, but probability of A different from 0 and probability of B different from 0, then you have the right hand side different from 0. But the left hand side is 0. So this is not true, right? And it's only true when you have probability of A equals 0 or probability of B equals 0, which is A is a zero measure set or B is a zero measure set. Okay. Okay, so we have an example here. I should put this. Okay. So toss two fair coins and define the event A is the event of head, tail, and B is head, tail, head, and C is head, tail, and tail, head. Can you show me that A and B are independent? A and C are independent. B and C are independent. How can we show A and B are independent? Just check use the definition. Check whatever we have probability of A intersect B equals to the product of probability of A times probability of B. Okay, so but what is the sample space in this case? Yeah. So the sample space in this case is omega is head, tail, head, and tail, right? We toss two fair coins, so we have 4 cases. So then now what is the probability of A intersect B? So this is A, this is A, and this is B. A intersect B is head, right? A intersect B is head. So you have the probability of head is 1/4, right? 1/4 because the sample space is you have 4 cases. And probability of A is you have 2 elements in A divided by 4 is the total number of the sample space, so which is you have 1/2. And the same with probability of B is also a half. Then check what is the probability of A intersect B. So we have it's 1/4, a quarter, and probability of A times probability of B also is a quarter. So okay, then A and B are independent. All right. How about C and A? So C and A is the same with the previous case. What is the intersect between A and C? The intersect between A and A intersect C is head tail, right? So this is the it's a bit, yeah, head tail. So then you can compute the probability of A intersect C is probability of head tail, which is a quarter, the same. And probability of C also is a half. And then you also have probability of A intersect B, A intersect C equal to probability of A times probability of C. Then you have A and C are independent. All right. And the same when you want to check whether for A and B, B and C. Okay. So the intersection of B intersect C is tail H, TH, right? Intersect of B intersect C. So probability of B intersect C is the probability of tail H, which is 1/4. And then you again can have this equality, which means that B and C are independent. Okay. Any question? No? Then there we have a property. This is a property of independence. So if we have A and B are independent, then it implies that A and B, complement of B, also independent. If A and B are independent, then A and complement of B also are independent. How can we prove it? So I have a picture for the case A and B, and then you need to show that A and B complements are independent. How can we show A and B complements are independent?
Write the definition, so probability of A can be equals probability of A multiplied by probability of B. Then use the fact that probability of B is just 1 minus its complement.
Complement.
And then you expand that and then just rearrange it such that you get the probability of A intersection B on the outside.
Okay, so I write what you said. Okay. So write because since A and B are independent, then you have probability of A intersect B equals to probability of A times probability of B, and then what? And then you write probability of B is 1 minus probability of B complement, is it? And then what's next? Expand this one, probability of A minus probability of A times probability of B complement, and then
multiply both sides by -1.
okay. So which means that yeah, and then
add probability of A to the left side.
okay, move the probability of A to the left side. So I have probability of A minus probability of A intersect B equals to probability of A times probability of B complement. And then what next?
So the left-hand side gives you probability of A intersect B complement.
Okay, probability of A minus probability of A intersect B. Okay, so this is A, and minus with probability of A intersect B, which is the yellow one. Then it is the probability of the green area, right? So which is the probability of A intersect with B complement equal to the right hand side. So now you see that you have the final equality, which is imply that A and B complements are independent. All right? Yep, thank you. So this is my proof. I tackle from the other way, but it's still the same result. So because I want to prove A and B complement are independent, so which means that I need to prove probability of A intersect B complement equal to probability of A times with probability of C complement. This is what I want to prove. So I start from the left hand side. I start from probability of A intersect B complement. So I want to rearrange this such that at the end I have this one. All right. Yes.
Why is it
Probability of A times with 1. The blue line or my proof? Which line? The purple one? Okay. Okay. So, okay, this one considered as a number. Probability of A is a number times 1 minus probability of A is a number times probability of B. So you take probability of A as a common factor outside of this. So you have this one. So then I go from the one I want to prove, which is probability of A intersect with B complement. Then A intersect with B complement equals to A is minus with the set A intersect B, right? And this one equals to probability of A minus probability of A intersect B. And then I use the I write here using. So I use the independence of A and B. Independent. So I have probability of A intersect B equals to probability of A times probability of B. And then I take probability of A outside as a common factor here. So I have probability of A times with 1 minus probability of B. And 1 minus probability of B is the probability of B complement. Okay, so now we complete the proof of if A and B are independent, so we can deduce that A and B complements also are independent. Do you have any questions? Okay. So we have a definition of two events are independent. So now we go to the definition of three events independence. So we have a definition that if we call A, B, C are independent if A, B, and C are pairwise independent and also certify that probability of A intersect B equals to the product of probability of A times probability of B times probability of C. And what does it mean when we say A, B, and C are pairwise independent? Which means that for any two, you pick any two events from A, B, C, you have their independence. Which means that in this case, when you say A, B, C independent, when you have, if you have A and B independent, which means that you have this equality, the first equality. And you have A, C are independent. B and C are independent. And then you have the last inequality. When you have all these four equality, then you can say that A, B, C are independent. Okay, so this is the definition of three events are independent. Yes?
So is there a time where they can be paired as independent if the intersection of all three isn't that?
No. So if A and B independent, then there is nothing to say about A and subset of B independent. We don't have any relation of that. Okay. So, do you have any idea for the general definition if we want to define nth event are independent?
It would be like all the events are pairwise independent.
Just pairwise. You mean that just only pick two? Yeah. Or any you pick 2, 3 up to n-1. They all need to be independent, and then you need to satisfy the last equality that the product of the intersection of all n events equal to the product of each one. So this is the definition of the general case. This is the definition of the general case. So if you have n event and they are independent if the probability of AI intersection of AI for I in a subset capital I equal to the product of probability of each element in this set I. And this set I is any subset of 1, 2, 3 up to n with at least 2 index. What does it mean? It means that, for example, we have 3, so 4. Go with an example for 4 events. Okay. So if we say we have 4 events, A1, A2, A3, A4, and then we say that they are independent if, so what is the condition for these 4 events are independent? So if we have A1, A2 independent, right? Any pair of 2 time with probability of A2. And then the same for A1, A3, A1, A4, A2, A3, A3, A4, right? So up to A3, A4 independent. And then you take 3 of elements in 4 here, 3 events in 4, so which is A1, A2, A3 independent, A1, A2, A4 independent, A2, A3, A4 independent, and then the last one is A1, 2, 3, 4 independent. So which means that you need to have this equality in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You need 10 equality to check whether A1, A2, A3, A4 are independent or not. All right. Okay. We have an example here to show that in this example, you will see that even A, B independent, B, C independent, A, C independent, which is A, B, C are pairwise independent, but A, B, C doesn't satisfy the last inequality, the last equality here. So they still are not independent from the definition. So this one comes from the one in here. So what is ABC? ABC is from this example. So what is the intersection of A intersect B and intersect C? A intersect B intersect C. Empty, right? A intersect B intersect C is empty. Okay, so we have probability of A intersect B and intersect C is empty, so which is 0. But probability of A, probability of B, and probability of C is a half for each, so the product is 1/8. But probability of A intersect B intersect C is 0, so you see that you cannot have the yellow inequality or the yellow equality here, this one. So which means that A, B, C are not independent. All right. Do you have any question? Okay, so we go to a definition for the conditional independence. So this is definition. Make his definition. Conditionally independence given C. So if probability of C different from 0, so we can say that A and B are conditionally independent given C if you have this equality. Which means that it is equivalent with the definition of two event independence, right? Now you see that you have A intersect B equals to probability of A times probability of B, but just with the conditional probability here, given C for each one. Okay, so when you check that probability of A intersect B given C equals to probability of A given C times with probability of B given C, then you can say that A and B are conditionally independent given C. So this is the definition. So we have a property for a conditionally independent. So if probability, so this one is a property of the definition. So if you have probability of A intersect C, B intersect C different from 0, so A and B are conditionally independent given C if and only if probability of A given B intersect C equal to the probability of A given C. So you need to prove this. Two sides, if and only if. So A and B are conditionally independent given C if and only if you have this equality. Okay, so we will try to prove this property of the conditional independent. can we prove it? Okay, so we prove this side first, which means that the left-hand side implies the right-hand side, which means that I assume that A and B are conditionally independent given C. Then I will prove that probability of A given B intersect C equal to probability of A given C. Okay, so this is the first side I want to prove. One thing is that is this probability make sense? Well defined. Can we define probability of A given C in this case? Is it well defined? Because we have probability of B intersect C different from 0 and probability of C greater than probability of B intersect C, right? Because we have from here, so you have probability of C greater or equal probability of B intersect C, because B intersect C is a subset of C. Right? So that's why probability of B intersect C less than or equals probability of C. And because you have this one greater than 0, which means that probability of C different from 0. So which means that probability of A given C is well defined. When you define a conditional probability, you need a condition that probability of the given event different from 0. So that's why we have it's well defined. Okay, so I go to the proof. So this is the statement, and then, okay, I prove. So now I want to prove that the first direction. If I have A and B are conditionally independent given C, I want to prove that A, B, C satisfy this equality. So to prove it, first I write down here is the definition of A, B are conditionally independent given C. So this is the definition of conditionally independent. So if A and B are conditionally independent, which means that I have probability of A intersect B given C equals to probability of A given C times with probability of B given C, right? This is from the definition of conditionally independent given C of A and B. Then, which means that if I divide both sides for if I divide both sides for this term, probability of B given C, I divide both sides for probability of B given C. So I have probability of A given C, this one from the right hand side, will equals to probability of A intersect B given C divided by probability of B given C, right? And now for the top, the blue term, I use the definition of conditional probability, right? It's just from the definition. Probability of A intersect B given C, the blue term here, equals to the blue term here, equals to probability of A intersect B intersect C divided by probability of C, right? And the denominator, the yellow term from the definition of conditional probability is equal to probability of B intersect C divided by probability of C. So the yellow term equal to this one. Just use the definition of conditional probability. And now you can see that you can simplify probability of C, right? Because probability of C different from 0. Everything is well defined, so we can cancel probability of C, simplify it. Then the fraction turn to the blue term on the top here divided by the yellow one. Probability of A intersect B intersect C divided by probability of B intersect C. So this one is the come from the definition. So you have this fraction is the probability of A given B intersect C. Right? So now at the end you can see that you have the red term equal to the red term at the end, which means that you can prove that probability of A given C equal to probability of A given B intersect C by using the conditional independent given C of A and B, and by using the fact that probability of C different from 0, probability of B intersect C different from 0. Do you have any questions? Is it clear? All right, how can we prove the inverse direction? Which means that the inverse direction, which means that we have this equality. When we have this equality, can we prove that A and B are conditionally independent given C? How can we prove that A and B are conditionally independent given C? Which means that you need to prove that. So you need to prove that probability of A intersect B given C equals to probability of A intersect C times with probability of B intersect C. So you need to prove the red line. So you have the equality in the red box, so you need to prove the red line. Can you see the solution? Just using all of these arguments. We did for the first step. It's not charged. Okay, that's fine. All right, how to prove it? Okay, look at this, the yellow, the blue box I make here is all equivalent steps, right? All of the arguments in the blue box is equivalent and only use the condition that probability of C different from 0, probability of B intersect C different from 0, right? All of the argument in the blue box. So then, to prove the inverse direction, I can say that since I have probability, since I have probability of A given B intersect C here equals to this one, equal to this one, right? What happened? Okay. Okay. So since I have this one equal to this one, its own equivalent from is there these own equivalent arguments. Just need a condition that probability of C different from 0, probability of B given C different from 0. So I say that since probability of B, A given B intersect C, which is this one, equals to the green one here. This one is the green one. And then because from the assumption, I have the left-hand side equals to probability of A given C, which means that I have these two equals. Right? This one equals to this one. So now look at this equality in the red box. You can see that you have what you want. You have just multiply both sides for probability of B given C. So you have probability of A intersect B given C equal to probability of A given C times with probability of B given C, which means that A and B are independent, conditionally independent given C. Okay, do you have any question? Okay, so we are finished the proof. I just want to make everything clear. Okay, then finish. All right. This is an example to see that independence does not imply conditional independence, and also in the previous way, which means that conditional independence doesn't imply independence. So you will see a lot of exercise, the same similar exercise as this one in the applied class. So you can practice to solve it at home or in the applied class. So I will not talk about it here. So we have 5 minutes left to learn about discrete random variables. All right. So we have for this is an example. This is an example. So if I let x be the number of heads out of 2 toes of a cone. If I let x be the number of heads out of 2 toes of a cone. So then what is the value of x and what is the, so x is a function, right? X will be a function mapping from the sample space into R, right? So the sample space we have head, tail, head, and tail. You have 4 cases, right? And then X is a mapping from the sample space into R. So for the first one, X will map head to 2 because it has 2 heads. Head tail to 1 because this event has one head. Tail head to 1 because you have 1 head. And tail to 0 because you don't have any head. So X is a mapping from the sample space into R. See? So we call X is a random variables. A random variable is a real value function defined on the sample space. So this is sample space, and this is the range of X. So X is the mapping from the sample space into R. And actually, X needs to satisfy the condition that it should be a measurable function. But in this code, we just ignore that. Okay. Not any function. Just remember that X cannot be any function. It has some condition for it. But in this code, we don't consider about it. So then this is an example for discrete random variable. So then we call X is a discrete random variable if the outcome is finite or countable infinite number of values. So it's called discrete. So now in this case, in this example, we call X is discrete because you can see that the range of X here just 1, 0, 1, 2. It's just finite number value in R. So it's called discrete. Another example is that if I let X is the number of heads until the first tail in the sequence of toes of a cone, this one. Then you can see that the sample space now is, what is it? It's the first time you flat the cone is the tail. And then the second one is that head and tail, right? And then head, tail, head, and then tail, so on. You can continue it. Then you can see here for this case,